There is a place at the outermost edge of the solar system where the sun is no longer a sun. It is just a star, the brightest one in the sky, but a star nonetheless, indistinguishable in quality from the 100 billion others spread across the galaxy around it. This place is real. It exists right now, surrounding the solar system in every direction like an enormous shell of frozen silence, and it contains an estimated 2 trillion objects made of ancient ice, drifting in almost complete darkness at temperatures just barely above absolute zero. It is called the Oort Cloud. Almost nothing that has ever been built has come close to reaching it. Tonight, you are going there. Welcome to Quiet Science at Bedtime, a storytelling channel where every journey is built entirely on real research and current scientific understanding. This channel is still very new, and if tonight's story gives you something, we would genuinely appreciate a subscription, a like, and a notification turned on. It helps more than you might think. Everything you are about to hear is based on real scientific fact. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Before you arrive, let the scale settle into you. The Oort Cloud begins at a distance of approximately 2,000 astronomical units from the Sun, 2,000 times the average distance from Earth to the Sun, which is itself 149,600,000 kilometers. The outer edge extends to approximately 100,000 astronomical units, and in some models as far as 200,000. That outer boundary is approximately 2 light-years from the Sun. The nearest star system, Alpha Centauri, is approximately 4.2 light-years away. The Oort Cloud extends nearly halfway to the nearest star. No spacecraft has ever reached it. Voyager 1, the most distant human-made object in existence, has been traveling since 1977 and is currently at approximately 168 astronomical units from the Sun. At its current speed of 17 kilometers per second, it will not reach the inner boundary of the Oort Cloud for another 300 years. It will not exit the outer boundary for approximately 30,000 years. This region of the solar system has never been observed directly. It was first proposed in 1950 by Dutch astronomer Jan Hendrik Oort, who noticed that long-period comets with orbital periods exceeding 200 years, arrived from all directions in the sky with nearly equal frequency. This isotropy, this lack of preferred direction, told Oort that their origin could not be the flattened disk of the solar system where the planets orbit. Their source had to be a vast spherical reservoir surrounding the entire solar system at enormous distance. He was right, and tonight you are there. You are aboard a vessel so small it casts no shadow worth measuring. It is a deep survey probe, autonomous and precise, built for one purpose: to station itself at 50,000 astronomical units from the Sun and take measurements. You have been traveling for what the ship's instruments record as 11 years. You stopped counting by calendar long before that. The probe's hull is made of a titanium alloy, reinforced with carbon fiber composite, approximately 8 millimeters thick. It maintains an interior temperature of 22 degrees Celsius through a closed-loop thermal regulation system running on a compact radioisotope power source, not dissimilar in principle to the RTGs that power Voyager 1, though smaller and more efficient by the improvements of decades. Without this system, the interior would equilibrate toward the ambient temperature of the surrounding environment. The ambient temperature outside this hull is approximately 4 Kelvin. 4 Kelvin is 4 degrees above absolute zero. Absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, is the theoretical lower limit of temperature, the point at which all molecular thermal motion ceases. The temperature outside this hull is not absolute zero, but it is close enough that the difference is almost philosophical. At 4 Kelvin, the molecules of any gas that happen to exist here would be moving at velocities so slow that a human hand could, in principle, outpace them walking at a brisk stride. 4 Kelvin is in fact very close to the temperature of the cosmic microwave background radiation, the thermal afterglow of the Big Bang, which permeates all of space at 2.725 Kelvin. The Oort cloud is so far from any significant heat source that the dominant thermal influence on its environment is the residual warmth of the universe's own birth, 14 billion years ago. You are in a place where the universe's oldest light sets the temperature. You look out the forward viewport. What you see requires a moment to understand. The stars are everywhere, not just above, not just to the sides, everywhere, distributed across the full sphere of the sky in every direction. This is because there is no sun to wash them out. From Earth, the sun's proximity and brightness bleaches the daytime sky into an opaque blue, making stars invisible for half of every 24 hours. Here, at 50,000 astronomical units, the sun is present. It is the brightest point source in the sky, but it is a point source, a star among stars. Its light, even here, is bright enough that looking directly at it without a filter would damage your eyes. But it does not illuminate the space around you. It does not brighten the sky. The sky has no atmosphere to scatter its light into. There is only the vacuum, and in the vacuum, there is only the direct light from each star traveling in straight lines until it hits a surface or a detector. The surface of your viewport is one such detector. The star field you see through it is the Milky Way from the inside, a band of increased stellar density running across the sky in one direction, with sparser but still numerous stars in every other direction. Approximately 5,000 stars are visible to the naked eye from Earth on the darkest nights. From here, that number is essentially the same. The human eye's sensitivity does not improve in vacuum, but the quality of each star is different. Each one is perfectly sharp. No atmospheric turbulence blurs or scintillates them. They do not twinkle. They are fixed points of light, exact and steady, as precise as calibration targets on a laboratory instrument. Among them, slightly brighter than the others, and entirely unremarkable in appearance, is the sun. You know which one it is only because the probe's navigation system highlights it with a faint cursor on the viewport's overlay display. Without that cursor, you would have to search. This is where you are, around the probe in every direction, moving so slowly that their motion is undetectable against the star field on any timescale a human being could directly observe, are the objects of the Oort cloud. The probe's instruments are detecting them. Not visually, they are far too dark and too cold to reflect meaningful light, but through thermal emission at infrared wavelengths, and through the extremely subtle gravitational perturbations their masses create in the fabric of space-time around them. The survey instrument aboard this probe is a next-generation infrared detector array operating at a detector temperature of less than 1 Kelvin, cooled by a closed-cycle cryostat to suppress thermal noise below the level of the signal it is trying to measure. The nearest Oort cloud object to your current position is approximately 12 million kilometers away. 12 million kilometers. The distance from Earth to the Moon is approximately 384,000 kilometers. The nearest Oort cloud object to this probe is 31 times the Earth-Moon distance away, and it is the nearest one. This is not unusual. This is the Oort cloud. The objects here are estimated to number in the trillions. Estimates range from 1 trillion to 10 trillion objects larger than 1 kilometer in diameter. The region they occupy is a sphere with a volume of approximately 10 to the power of 33 cubic kilometers. Distributing even 10 trillion objects across that volume yields an average spacing of roughly 50 to 100 million kilometers between neighbors. The Oort cloud is not a dense cloud in any physical sense. It is a sparse, three-dimensional scattering of frozen objects, so widely separated that the word cloud is almost misleading. It is more like a statistical population, a probability distribution of matter, than anything you could look at and call a cloud. And yet, by mass, it represents a significant reservoir of the solar system's primordial material. The objects in the Oort cloud are ancient. They are estimated to be approximately 4.5 billion years old, the same age as the solar system itself, formed from the same rotating disk of gas and dust that produced the sun, the planets, and everything else orbiting within a few hundred astronomical units of the center. The solar system formed through a process called accretion. Dust grains in the protoplanetary disk collided and stuck together, growing over millions of years into larger and larger bodies, eventually forming planetesimals, objects tens to hundreds of kilometers across, which then collided and merged further into the planets we have today. During this period, the giant planets, particularly Jupiter and Saturn, dominated the gravitational dynamics of the inner solar system. Their enormous masses, their orbital resonances, and their gravitational interactions scattered vast numbers of planetesimals outward, flinging them onto trajectories that took them away from the sun on elongated elliptical paths. Many of these scattered objects were ejected from the solar system entirely, achieving hyperbolic trajectories and escaping into interstellar space. But some fell into a range of trajectories that were then perturbed by the gravitational influence of passing stars and the galactic tide, the DARB's differential gravitational force exerted by the mass distribution of the Milky Way galaxy itself, and had their orbits circularized into the roughly spherical shell we now call the Oort cloud. The objects that make up the Oort cloud are, in a real sense, the solar system's discarded material, the fragments that the giant planets could not incorporate and could not fully eject. They have been orbiting here in this cold darkness for 4.5 billion years, unchanged for the most part, unprocessed. The surface layers of some of the larger objects may have been altered by cosmic ray bombardment, which creates a thin radiation-processed crust of complex organic molecules. But beneath that crust, the material is pristine, a frozen sample of the molecular cloud from which the solar system formed, preserved in these conditions for longer than the Earth has had complex life. You reach out and place your gloved hand on the interior wall of the hull. On the other side of 8 millimeters of titanium alloy, separated from you by that distance and nothing else, is 4 Kelvin vacuum, and 12 million kilometers away in it is a fragment of the original solar system, exactly as it was 4.5 billion years ago. You leave the hand where it is for a moment. Let us talk about what these objects are made of. The composition of Oort cloud objects has not been directly measured. No probe has ever sampled one, but their composition is inferred from two sources: the spectroscopic analysis of long-period comets that originate in the Oort cloud and travel inward through the solar system, and the theoretical models of solar system formation that predict what kinds of material would have been available at the distances where these objects formed. The results from both sources are consistent. Oort cloud objects are composed primarily of water ice, frozen H2O, the same molecule that makes up Earth's oceans and polar ice caps. Water ice is the most abundant solid-state condensate in the outer solar system because water's freezing point under the low pressures of space is approximately 150 Kelvin, which means it freezes at distances beyond the frost line, the boundary in the protoplanetary disk, inside which water existed as vapor, and outside which it could condense as solid ice. The frost line in the early solar system was located at approximately 2 to 3 astronomical units from the Sun, roughly between the orbits of Mars and Jupiter. Mixed with the water ice are frozen ammonia, NH3, with a sublimation temperature of approximately 78 Kelvin under vacuum conditions. Frozen carbon dioxide, CO2, sublimating at around 72 Kelvin. Frozen carbon monoxide, Colorado, sublimating at approximately 25 Kelvin. Frozen methane, CH4, at around 31 Kelvin. And embedded throughout all of these ices, silicate dust grains, carbonaceous material, and complex organic molecules, hydrocarbons, aldehydes, alcohols, and amino acid precursors, synthesized in the interstellar molecular cloud before the solar system even formed. The object 12 million kilometers from your probe contains all of these things. It is a frozen archive of pre-solar chemistry, of the molecular composition of the nebula that became this solar system, locked in ice at 4 Kelvin for 4.5 billion years. When a gravitational perturbation from a passing star nudges an object like this into an elongated orbit that eventually brings it into the inner solar system, it approaches the Sun. At around 3 to 5 astronomical units from the Sun, the surface temperature rises enough for carbon monoxide and carbon dioxide to begin sublimating. The released gas carries dust grains with it. The object develops a coma, a diffuse atmosphere of gas and dust. Solar radiation pressure and the solar wind push this coma away from the Sun, forming a tail. The object becomes a comet. Halley's Comet, one of the most studied comets in history, with recorded observations dating back to at least 240 BCE in Chinese astronomical records, is a short-period comet with an orbital period of approximately 75 years, likely originating from the Kuiper Belt rather than the Oort Cloud. But the long-period comets, those with orbital periods of thousands or millions of years, arriving from random directions in the sky, are almost certainly Oort Cloud objects on their first approach to the Sun, still carrying the pristine material from 4.5 billion years ago. Each time you have seen a comet in the night sky, you were looking at the Oort Cloud announcing itself. Outside the viewport, nothing moves on any timescale you can perceive. The star field is static. The probe's instruments record motion, but on scales your eyes cannot resolve. The nearest Oort Cloud object is moving at approximately 150 meters per second relative to the Sun. 150 meters per second, approximately 540 kilometers per hour, roughly the cruising speed of a commercial aircraft. This seems fast until you remember the scale. At this speed, crossing the 12 million kilometers to the nearest neighbor would take approximately 926 hours, 38 days of continuous travel at aircraft cruising speed. The object's orbital period, the time required to complete one full orbit around the Sun, is estimated at approximately 5 million years. 5 million years ago on Earth, the genus Australopithecus was just appearing in Africa. The hominid lineage that would eventually produce modern humans was in its earliest stages. That orbital period is not a long time in geological terms. The Earth has been here for nearly 1,000 such orbits. But it is a duration so far beyond the scale of human civilization that it functions, for practical purposes, as permanence. These objects do not hurry. They do not need to. They have been doing this for 4.5 billion years. They will be doing it for billions more. This is a place defined by patience and by a cold and thorough stillness that has nothing in it of violence or urgency. The Oort Cloud does not press on anything. It simply is, surrounding the solar system in every direction, at distances so vast that the sun that formed it and the planets it shelters are reduced to points of light, indistinguishable from all the other points of light in the sky. Your breathing has slowed inside the suit. You notice it without meaning to. Here is what Jan Hendrik Oort actually did in 1950, and why it matters. Oort was working at Leiden Observatory in the Netherlands, where he had spent decades studying the structure and dynamics of the Milky Way galaxy. In 1950, he turned his attention to a dataset of long-period comets with orbital periods too long to have been observed more than once in recorded history. He analyzed the original orbital energies of these comets, tracing their paths backward to determine where they had come from before entering the inner solar system. What he found was striking. The distribution of original orbital energies was sharply concentrated near zero, meaning the comets had come from enormous distances, approaching the sun on nearly parabolic trajectories that indicated they had started their journey with almost no kinetic energy relative to the sun. They were falling inward from very, very far away, and critically, they were coming from all directions equally. No preferred plane, no preferred direction. From this analysis, Oort concluded that the solar system is surrounded by a vast, roughly spherical reservoir of cometary nuclei at distances of tens of thousands of astronomical units, and that these objects are occasionally perturbed into sun-approaching trajectories by the gravitational influence of passing stars. He estimated the population at approximately 10 to the 11th power, 100 billion objects. Modern estimates based on improved modeling of the solar system's formation history and on the observed flux of long-period comets range from 1 trillion to 2 trillion objects larger than 1 kilometer in diameter, with the total mass of the Oort Cloud estimated at somewhere between 1 and a few tens of Earth masses. These estimates are uncertain. The Oort Cloud has never been directly imaged. No telescope built by humanity has sufficient sensitivity to detect an Oort Cloud object at its nominal distance. The entire body of knowledge about this region rests on inference, on what the comets tell us when they arrive, on what the formation models predict, on the mathematics of orbital dynamics applied backward through time. You are the first instrument ever placed here. The probe's survey data is being transmitted back to Earth at the speed of light. The signal takes approximately 29 days to arrive. 50,000 astronomical units divided by the speed of light in astronomical units per day. A round-trip communication takes nearly 2 months. You sent a query about the nearest object's composition 3 weeks ago. You are still waiting for the uplink command response that will adjust the spectrometer's integration parameters. In this place, patience is not a virtue. It is a physical requirement. The galactic tide is something you can measure from here. Physical requirement. On Earth, tidal forces are associated with the moon and, to a lesser extent, the sun. The moon's gravity is slightly stronger on the side of Earth facing the moon than on the far side, producing a differential force, a tidal force, that stretches the Earth very slightly along the Earth-Moon axis and produces the twice-daily ocean tides that have governed navigation and biology for the entire history of life on the planet. The same physics operates on a vastly larger scale. The Milky Way galaxy contains a mass of approximately 1 trillion solar masses, distributed in a disk structure approximately 100,000 light-years in diameter, and a few thousand light-years thick. As the solar system orbits the galactic center, one full orbit taking approximately 225 million years at an orbital velocity of approximately 230 kilometers per second, the differential gravitational force of the galactic mass distribution acts on the extended structure of the Oort Cloud. This galactic tidal force is not negligible at Oort Cloud distances. It is in fact the dominant perturbative force acting on the outer Oort Cloud, more significant than the gravitational influence of the planets, and comparable to or greater than the perturbations from passing stars. The galactic tide continuously deforms the orbits of Oort Cloud objects, pulling some of them onto trajectories with smaller perihelia, smaller closest approaches to the Sun, effectively feeding the inner solar system with comets at a slow, continuous rate determined by the geometry of the galactic orbit. The solar system is not isolated, it is embedded in a galaxy, and the galaxy acts on it. The comets that arrive in the inner solar system, that develop tails and become visible from Earth, that have been recorded in historical chronicles across human civilizations, they are arriving because of the differential gravity of 100 billion stars distributed across a disk 100,000 light-years wide. Every comet you have ever seen was gravitationally launched by the Milky Way. The probe's thermal management system cycles quietly in the background. You can hear it, a faint, regular sound in the otherwise complete silence of the interior. One cycle every 90 seconds. The sound is familiar now in the way that all sounds in an enclosed space become familiar after months and years. You stopped consciously hearing it long ago. It is approximately 22 hours into the current data acquisition period. The infrared survey instrument has been running without interruption for the full 22 hours, accumulating signal from the thermal emission of nearby Oort Cloud objects. Each additional hour of integration improves the signal-to-noise ratio by the square root of 1, meaning that to double the sensitivity of a measurement, you must quadruple the observation time. Long surveys in astronomy are not about patience in a poetic sense. They are about the mathematics of noise reduction. You run the instrument longer because the universe's signal is faint, and the only way to hear a faint signal is to listen for a very long time. The instrument is listening. You close your eyes for a moment, not to sleep, you are not yet ready for that, but because the star field, beautiful as it is, offers no information that you are not already receiving from the instruments. The instruments are the senses of this mission. Your eyes are supplementary. Behind your closed eyelids, there is nothing but the darkness of the inside of your own skull, and in that darkness, the brain does what it always does in low stimulation environments. It begins to process, to sort, to rehearse and consolidate the information accumulated through the day. The hippocampus, that seahorse-shaped structure on the medial surface of each temporal lobe, approximately 5 centimeters long, does not wait for sleep to begin consolidating memory. In quiet waking states, with the flow of new sensory information reduced, the hippocampus engages in offline processing, replaying recent experiences at accelerated speeds through the same neural circuits that were active during acquisition. This is one reason why rest, even awake rest, with eyes closed and stimulation minimized, measurably improves memory retention compared to continuous activity. You have been in a low stimulation environment for 11 years. Your memory of Earth, of the people you knew there, of the texture of outdoor air and the sound of wind in actual trees, has been consolidating and reconsolidating for 11 years in the quietest environment a human being has ever occupied. What you remember of those things is very clear. Strangely, precisely clear. You open your eyes again. The star field is unchanged. Of course it is unchanged. The nearest star other than the Sun, excluding the Sun itself from the count, is Proxima Centauri at 4.2 light-years, which at the proper motion of approximately 3.85 arcseconds per year relative to the solar system would not have moved by any amount detectable by your eyes in the time your eyelids were closed. The stars do not move on human timescales, not visibly. The apparent constancy of the star field was what allowed ancient navigators to use the stars as a fixed reference for position finding on Earth's oceans. It is what allows this probe's star tracker to use Canopus as an orientation reference, the same way Voyager 1 has used it since 1977. The stars appear fixed because they are, for practical purposes, infinitely far away relative to any motion occurring on human timescales. But they are not actually fixed. Every star in the galaxy is orbiting the galactic center on its own path, at its own speed, in its own direction. The apparent constancy of the star field is an illusion created by distance and the brevity of human timescales. Given enough time, tens of thousands of years, hundreds of thousands of years, the constellations visible from Earth would be unrecognizable. Orion would dissolve. Ursa Major would rearrange. The familiar patterns are temporary arrangements of stars that happen to be roughly aligned in our line of sight at this particular moment in the galaxy's history. Here, at 50,000 astronomical units, the star field looks almost identical to what it looks like from Earth. The angular shift, the parallax, produced by moving from Earth's position to this position, is approximately 1 in 14,000ths arcseconds for the nearest stars and immeasurably small for distant ones. The Oort Cloud is still well within the solar system in galactic terms. You have not moved far enough to change the view of the galaxy. The same stars you would see from Earth are watching you now. The probe enters its scheduled low-power cycle. This happens every 96 hours, a 4-hour window in which non-critical systems are powered down and the main computer enters a reduced activity state to allow heat-producing components to cool and extend their operational lifespan. You have experienced this cycle hundreds of times. You know its rhythm. The interior lighting dims from its standard operating level to approximately 3% of maximum, just enough to navigate if you need to. The ventilation system reduces to a lower flow rate. The background acoustic environment of the probe, already minimal, becomes quieter still. The hum of the infrared instrument's cooling system, however, continues. The instrument does not pause. The survey does not pause. Only the less essential things go quiet. You find this restful. The 4-hour low-power window has become, over years of repetition, the period in which you sleep most deeply. Not because the reduced lighting signals your circadian system to produce melatonin. The probe's interior lighting is calibrated to support normal circadian function, regardless of the cycle, but because something in the reduction of ambient sound and activity creates a condition the nervous system interprets as permission to stop monitoring, permission to let the instruments do their work without supervision, permission to be horizontal and still in the dark, while the probe continues its patient survey of a region of space that has been silent and undisturbed for 4.5 billion years. Outside, at 12 million kilometers, the nearest Oort Cloud object drifts along its ancient orbit, indifferent to your presence. Inside, the delta waves are beginning. Stage 3 non-REM sleep, slow wave sleep, is the stage in which the brain's electrical activity reaches its most synchronized state. The cortical neurons that spend waking hours firing in complex, asynchronous patterns, the neural correlate of perception, cognition, and conscious experience, begin firing together in slow, rolling waves below 4 cycles per second. These delta waves propagate across the cortex in organized fronts, visible on electroencephalography as large, regular, high-amplitude oscillations. The synchrony is the point. When neurons fire together in this pattern, the firing is not encoding new information or processing sensory input. It is doing something else, consolidating the structure of memory, clearing the molecular debris of waking metabolism, and allowing the restorative processes that cannot run efficiently during wakeful neural activity to do their work undisturbed. The glymphatic system, first described in the published scientific literature in 2012 by Macon Nedergaard and colleagues at the University of Rochester Medical Center, is one of those restorative processes. During slow-wave sleep, astrocytes, the support cells of the brain, contract by up to 60% of their waking volume. This contraction expands the interstitial space between neurons, allowing cerebrospinal fluid to flow more freely through the brain tissue. The fluid circulation flushes accumulated proteins, including beta amyloid, the protein whose aggregation is associated with the neurodegeneration of Alzheimer's disease, into the venous drainage system. The brain washes itself during slow-wave sleep. This process cannot occur at full efficiency during waking because the neural activity required for consciousness physically restricts the flow of cerebrospinal fluid through the interstitial space. The brain must go quiet, must reach the synchronized low-activity state of deep sleep for the maintenance cycle to run. Outside the hull, the Oort Cloud maintains its own kind of maintenance. The objects here are not colliding, not processing, not changing in any way detectable on human timescales. They are simply present, in the cold and the dark, in the condition in which they have existed for longer than complex life has existed on Earth. Their preservation is a function of this exact environment, cold enough to prevent sublimation of even the most volatile ices, sparse enough to prevent collisions, distant enough from the sun that radiation processing is minimal. The Oort Cloud persists because nothing disturbs it. It rests, in the most literal physical sense, in conditions optimized for preservation. Your brain is now doing something similar, clearing, preserving, preparing the structures that will carry tonight's experience forward into the days and weeks and years ahead. Let it run. Your pituitary gland is releasing growth hormone now. This small structure, approximately 8 millimeters long and suspended from the underside of the hypothalamus by a thin stalk called the infundibulum, releases its largest daily pulse of growth hormone within the first 90 minutes of slow-wave sleep onset. In adults, growth hormone does not drive height increase as it does in childhood and adolescence. It regulates protein synthesis, cellular repair, fat metabolism, and the maintenance of muscle and bone tissue. Approximately 70% of the daily growth hormone secretion in adults occurs during this first deep sleep episode. Your body is repairing itself. The cellular processes that accumulate damage during waking hours, oxidative stress on mitochondria, protein misfolding, DNA strand breaks from the normal chemistry of metabolism and from background radiation, are being addressed by repair mechanisms that run most effectively during the low metabolic demand state of slow-wave sleep. In the Oort Cloud outside, the cosmic radiation environment is slightly more intense than inside the heliosphere, where the solar wind's magnetic field provides partial shielding from galactic cosmic rays. The probe's hull provides additional shielding. Your body receives a slightly elevated radiation dose here compared to Earth, carefully within acceptable mission parameters. Some of that radiation causes double-strand breaks in DNA, the most severe form of DNA damage, in which both strands of the double helix are severed. These breaks are repaired by molecular machinery in the cell nucleus, the non-homologous end-joining pathway, and the homologous recombination pathway, which use the undamaged strand or a sister chromatid as a template to restore the original sequence. These repairs are happening right now in cells throughout your body, while the delta waves roll through your cortex and the probe's instruments accumulate signal in the interstellar dark. The universe is not gentle, but life has built elaborate systems to persist within it. Somewhere in the slow-wave sleep cycle, the first REM episode is approaching. Rapid eye movement sleep was first systematically described in 1953 by Nathaniel Kleitman and Eugenia Sarinsky at the University of Chicago. It is the stage most associated with vivid dreaming, characterized by low-amplitude, high-frequency brain activity resembling wakefulness, combined with the active paralysis of voluntary muscles. The pons, a structure in the brainstem, generates rhythmic bursts of electrical activity that propagate upward through the thalamus to the visual cortex, producing the neural substrate for visual experience in the absence of visual input. In REM sleep, the prefrontal cortex, the region most associated with rational, analytical thought, with planning, and with the critical evaluation of experience, is less active than during waking. Other regions, including the limbic structures involved in emotional processing, are relatively more active. This shift in the balance of neural activity is thought to contribute to the associative, emotionally resonant quality of dream experience. The connections made in dreams are not the connections analytical cognition would make, but they are connections nonetheless, and some fraction of them are useful. You may dream of what you have been here, of the star field through the viewport, of the measurement of an object 12 million kilometers away by its thermal emission at wavelengths your eyes cannot see, of the galactic tide, a differential gravitational force spanning 100,000 light-years, slowly and continuously reshaping the orbits of 2 trillion frozen fragments of the original solar system, of Jan Oort at Leiden in 1950, tracing comets backward through their orbital mathematics to find a reservoir no telescope had yet seen, of the sun reduced to its proper scale, 1 star among 100 billion, the brightest in this particular sky only because of the accident of proximity, 4.6 billion years in the making. If you dream of these things, that is not imagination unmoored from fact. That is the dreaming brain applying its particular kind of processing to the science of this place, finding the connections that the waking analytical mind might have noted but not fully felt. Let it work, a typical night of sleep cycles through 4 to 6 complete 90-minute cycles. In the early cycles, slow-wave sleep dominates. In the later cycles, REM episodes grow longer. The final REM episode of the night, in the last hour before waking, may last up to 45 to 60 minutes. Through all of these cycles, the probe outside continues its work. The infrared detector array has now been running for 26 hours. The signal-to-noise ratio has improved by the square root of 26 over the 1-hour baseline. Each additional hour makes the faint thermal emission of distant objects a fraction more detectable above the noise floor of the instrument. The probe does not need you to be awake to do this work. The survey runs on its own, storing data to the onboard memory, compressing it according to preloaded algorithms, and queuing it for transmission back to Earth in the next scheduled downlink window. The probe was built to work while you rest. Everything you have observed and measured and recorded here, everything in the survey data accumulated over 11 years, it is all being transmitted back at the speed of light to the people who built this mission, who are reading the data and building the first empirical picture of the Oort Cloud from an instrument placed inside it. They are sleeping too, most of them, in whatever time zone their particular city occupies. The data arrives at the receiving station automatically. It is archived automatically. It will be analyzed when the scientists wake up and go to their desks. Science does not require constant waking attention. It requires careful instruments, careful design, and the patience to let the process run. The probe is running. Your body is running. Both are doing exactly what they were designed to do. Let the words slow now. The object at 12 million kilometers is still drifting, still carrying its water ice and its frozen carbon monoxide and its silicate dust and its pre-solar organic molecules on an orbit that takes 5 million years to complete. It has completed this orbit approximately 900 times since it formed. It will complete it many hundreds of times more before any perturbation reaches it from a passing star or from the galactic tide. And when that perturbation comes, over thousands of years, gradually nudging its orbital parameters toward a smaller perihelion, eventually sending it inward on a journey that will take thousands of years more to complete, it will arrive in the inner solar system. It will sublimate. It will develop a coma and a tail. It will be visible from some planet to whoever or whatever is there to see it. It will carry the chemistry of the presolar nebula into the light for the first time. That event is roughly 5 million years away, or 10 million, or 50 million. The uncertainty in the timeline is larger than the duration of human civilization by many orders of magnitude. There is no hurry. There is no hurry in any part of this place. Let that register fully. No hurry, no deadline, no threshold that must be crossed before morning. The delta waves are yours. Threshold that must be crossed. The universe's oldest light, the cosmic microwave background at 2.725 Kelvin, fills the space outside the hull in every direction, the same as it fills every space in the observable universe, the same as it passes through this vessel's walls, and through every structure on Earth, and through every sleeping person on the planet right now. It has been traveling since 380,000 years after the Big Bang. It will be traveling for billions of years more. It passes through you. Let it. Stage 3. Delta waves. 4 Kelvin outside. 22 degrees in here. The breath is slow. 1 cycle every 4 seconds or so. 500 milliliters in. 500 milliliters out. The diaphragm moving with the automatic precision of the pre-Boetzinger complex in the medulla oblongata, which has been generating the respiratory rhythm without conscious instruction since the moment you were born. The heart is steady, 53 beats per minute perhaps 50, 70 milliliters per beat. The circulation continuous, everything is running, you do not have to watch it. If you are still awake to hear these words, then here is what you found tonight. You traveled to the outermost region of the solar system, a place no probe has ever reached, a region proposed by a Dutch astronomer in 1950 from the analysis of cometary orbits, a sphere of frozen ancient material surrounding the entire solar system at distances up to 2 light-years from the Sun. You learned that the objects there are 4.5 billion years old, the preserved chemistry of the pre-solar nebula, unchanged in the cold and dark since before the Earth existed. You measured the nearest neighbor at 12 million kilometers. You felt the scale of a place where the Sun is just a star, and the dominant thermal influence on the environment is the warmth left over from the Big Bang 14 billion years ago. You learned that your brain, while you sleep, washes itself, repairs itself, and consolidates what you have learned. That this happens automatically through systems refined over hundreds of millions of years of evolutionary history in conditions that do not require your management or your attention. You learned that patience is not a quality the Oort Cloud possesses because it is wise. It is a quality the Oort Cloud possesses because it exists at a scale where human urgency has no relevance. Nothing there hurries, nothing there is late, and for a few hours tonight, neither are you. If this journey brought you something, stillness, or a sense of the vast and quiet scale of the solar system, or simply the familiar weight of closed eyes, we hope you will return. Quiet Science at Bedtime is still a very new channel. Every subscription, every like, every notification turned on is a direct and concrete act of support that makes the next journey possible. If you are still awake enough to do it, thank you. Please subscribe, please leave a like, and if you are already asleep, then you arrived at exactly the right moment. The probe is still running, the survey is still accumulating, the Oort Cloud is still there. 4 Kelvin and silent, surrounding everything. Sleep well. Good night.